All right. Oh, we have screens on both ends. Naveed, really good to see you. I feel like I'm waving to you from across the room, but but you're much closer. All right. All right. Well, that was fun. Computer technology enables new experiences every day that are surprising and exciting. Hold this closer. There we go. Now it's, ooh, that's pretty cool. All right. So we're going to do this in a kind of an open way. So if people have questions, like think about them. We'll call on a few people, and then I've asked Raja and Mateo to think about a question to ask each other. We're going to go around a little bit and talk. Um, but the first question really is, um, Raja, maybe you can kick this off. Is RISC-V real? Like, is it happening?
So is RISC-V real? Is
Raja,
it
maybe you can kick this off. Is RISC-V real? Like, is it happening?
good? So the question, um, the discussion starter is RISC-V real? So five as a GPU command front end. In 2016 timeframe we started, and I think that GPU shipped in 2017-ish. And since then, multiple generations of GPUs from AMD and even NVIDIA have used the RISC-V as a front end. So that the potential to take a open source IP and for users where you needed a general purpose like processor, a decent performance with decent tool chain, that was very clear. So I know most people here know that RISC-V has been a success in embedded and controllers and all. So I'll leave that aside and focus on, is RISC-V real for all the rest of general purpose computing? And that's been a question mark on lots of people's minds, right? While there is a lot of momentum and all. And to me, when I saw, I think it was demoed yesterday, but I also saw it at the Tenstorrent office when the Bodhi computing guys demonstrated a real web server running on the full RISC-V QEMU, the emulation environment. As a product engineer, to me that's like pretty damn close to real. Okay, so the next step is seeing something like that running on real silicon, which I believe is the question is when. Okay, so I think the question in everybody's mind is it 23, 24, 25? Pick a year, right? The only it's just a matter of time. So that's kind of my perspective on RISC-V real or not, but I'd like to hear other thoughts.
I agree with you. By the way, good morning to everyone. It's my pleasure to be here with you. I am enjoying and I am charging my battery with the energy you produce. So I am very happy at my age. So I think it's a reality, okay? So I am very old. So when I I was the dean of the computer science faculty in '83. I had to buy a computer. At that time, when you bought a computer, you bought the software and the hardware. The software was unable to be executed in another hardware, okay? Linux democratized that. And now with RISC-V, we democratize the hardware. So we have an open environment where we can collaborate. So for me, RISC-V, as you know, is nothing special in computer architecture. In fact, they changed a bit for the MIPS. MIPS could have been a RISC-V. The time when RISC-V arrived was the right time because it's the time where at the university we were able to tape out chips and to demonstrate that. So I think it's a reality and it's the only way we are having, and I think my prediction in the future, in a short future, probably the only thing we are going to have is RISC-V worldwide in a short time, because nobody can go against the humanity. And we listen how we can collaborate now, how we are doing things together, how we can bring our ideas to the hardware, to the software. it's a unique opportunity. So welcome, RISC-V.
That's great. And if our technical difficulties can be overcome, I'd like to ask Naveed to comment because he was advocating and pushing RISC-V when many people in the world hadn't heard about it. And he was very tireless of advocating that as part of Sci-Fi and some other adventures. Naveed, can you comment on how the world's changed in the last couple of years about RISC-V? Because you've been there for the whole journey. Oh, no. Naveed, can you comment on those?
Can you guys hear?
Yeah. Yes.
In all, not just, embedded and laptops but all the way into data center. I believe that is happening now. I think RISC-V is a reality today. And I think there are so many companies that have been created and so many people around the world. Data center. I believe India, in China, that is happening now. I think RISC-V is a reality today. And this is a
All right, we almost got through that perfectly. Bob? Bob, by the way, could you guys mark that place in the video? Because what he just said was the most important thing in this conference. We cannot collaborate, we cannot innovate. So ARM was doing such a great job, but I work with that great company. They wouldn't do simple things we wanted. They wouldn't let us do what we wanted for them, which is a crazy making thing. But Srikant, I'm looking at you. There's some IP and collateral we're building. We got to go figure out how to release that to people so they can collaborate. I talked to a whole bunch of students last night, which, by the way, thanks for coming. You guys are super fun. It's inspirational and it reminds me of my responsibility to work with young people and actually do stuff, but create the ability to collaborate. That's and they brought up a bunch of interesting points. Oh no. Naveed, if you can hear me, the screens just went out. Yeah.
I can hear you.
Yeah.
I can hear you.
So yeah, I really like that point because I had heard RISC-V as the opportunity to change the business model and the cost model, and you said that's not what anybody cared about. They wanted to collaborate and innovate. That's really perfect. So I really appreciate that's super clear.
And then the second part of my comment, I said, I met with Raja and the Intel team in 2018 and 2028. RISC-V will be prevalent in all, all the way from embedded to servers. I think we are on track. I think maybe ahead of what I had predicted. I think we might toward had predicted.
Yeah. I believe.
and this is very important, how we can collaborate. Just professional computer architecture. So during many years, we just have ideas, we evaluate with simulator, but we were unable to implement that. Now, with RISC-V, for example, we have extra instruction for in the vector architecture to deal with database, for example. This is a unique opportunity, and we can share this. Nobody will stop that. Nobody stop the Linux. When I installed the first supercomputer in Barcelona in 2004, it was the first supercomputer with Linux. And people, you are fool, Mateo. You will fail. No. Nobody can go against the world. Nobody can go. And it's very clear. For me, it's very clear.
So my question, which I get asked, and I've heard many people ask, but you see, this collaboration and innovation, all that stuff is great, and of course, this is a room full of nerds. That feels good, but this room full of nerds are funded by some people writing checks, right? So how is the RISC-V community, the RISC-V ecosystem, going to make money? What's the business model? Like, how is it, where is the money?
Because we had an interesting experience. So we started with RISC-V in our AI processor because we needed to make low-level modifications that are somewhat novel to a computer, right? So we made we call it the baby RISC. We stripped out some functionality. We added semaphores so we can have 5 processors running in parallel, but they can also interlock with each other in novel ways. And it's very bespoke to our problem, right? And then we talked to a bunch of people and they said, we want compute next to your AI processor in the same chip because I want to run this graph and then have it jump into a C program and like sort the output of a softmax or something. And so we said novel conversions from float to int and back because we care a lot about how the precision of the operations happen. We have big accumulators for small data types. There's a bunch of novel stuff, right? But it amounts to 1% of a processor area. It's not complicated, it's just necessary. And ARM said no. So we went to Sci-Fi, great company. They said, sure, we'll do it. We said, we'll write the RTL for you. They said, no, we got it, it's easy. We'll just put it in. They just put it in the next release. Like, it was so funny. So then we said, hey, we have some applications where we want to build a high performance processor, and we talked to our investors, and they said, we think there is value in a high performance processor. So we literally raised money on the idea that high performance RISC processors would give us additional benefit, right? And then we showed that to people. We were talking about AI roadmap. And this is my surprise. They said, we like your AI chip, Jim, but could we buy your RISC-V processor, right? This was not an outbound marketing plan. I'm not a marketing guy. I have crazy ideas and stuff, but I'm mostly a technologist. And multiple people said they want to purchase our processor. And then the question is how, right? So there's IP, there's chiplet, there's chip, there's multiple places. And we realized really quickly there are so many people who need a range of processors, and the cool thing about RISC-V is you want a tiny one, you can get one. You want a free one, you can get one. You want to buy a processor with support from a company, knows how to support issues. Like, there's different reasons to use free or to buy. And there was a place in the market for a high-end processor, and ours is 8-wide, out-of-order issue, but it's somewhat optimized for big data stuff. So we have a very large L1 cache. We don't really have an L2 cache. We made a bunch of decisions for streaming data. That may be different from a server. And people said, we like that. So how do we make money? People come to us and they said, can I buy that IP? And Keith Wittick, who's going to talk a little bit about customers today, is our COO. We're working on multiple deals where they are more than funding our development costs because they want to be able to have a processor, and get this, that they could buy from us and then make their own changes and then keep and use in their products, right? Which you can't do from ARM or from Intel or from AMD. So how do we make money? We create value that people actually want. They want to pay me to do the work, and the ROI is positive. Like, it's pretty straightforward.
So Mateo, I'll frame it for you the same question because you're, for those folks who don't know about Mateo, he's a professor, okay? He's an architect, but he's also the most successful fundraiser I have seen, money raiser, and how is
I,
RISC-V
I
helping?
didn't get money from him. It was impossible. No, I mean, no, I mean, I fully agree with you. I think that, especially now when the technology is approaching, I think we can discuss about that to the end of the Moore's law. The RISC-V is the mechanism that allows us to bring our ideas to the reality. So the customization will be the way we will use, just answering your question, to capitalize our ideas. And you put many examples, I fully agree with you. The same happened in the field of supercomputer. We can do things. The applications are changing very quickly. So we can produce chips, adapting the hardware to the application. It was almost impossible until now because the machinery from the big companies were very slow, not to adapt the reality to the hardware, to the software. We can do co-design. And in the field of supercomputers, I had been many years there, it was impossible. You were able to go from the application, algorithm, programming, but when you reach the hardware, nobody was talking to you. Now you can talk down, and then that will allow you to improve a lot the supercomputer application, the supercomputer center. So I am very happy about that.
Naveed, any comments?
So, yes, certainly. I think there are three constituents, Raja, in your question. Constituent number one, investors. Constituent number two, IP companies. Constituent number three, IP users. Right? How do they all make money? So I'll just simply say, Jim already answered the question for IP producers. He is one of the IP producers. As long as the thing about RISC-V IP is going to be, that's going to be a treadmill. We do not have, any secrecy. So as a result, what will happen is that if Jim wants to be in IP business, he has to keep on producing better and better cores to keep on making money. You cannot stay stagnant and make money. So that is for the people like Sci-Fi and Tenstorrent and other people who are selling IP. So that's one constituency. So it's unlike ARM or even unlike Intel or other people, where you could sit on something for some time and milk it. In RISC-V, you can't milk it. You have to be on a treadmill. You keep on having to produce something better and better every year. That's the only way you sell. Otherwise, other people catch up. For investors at Sci-Fi, if you remember, we created 5 companies. Today, I think they are worth around close to $5 billion together, those 5 companies. If you put in Tenstorrent and many other companies, I think the number could be close to maybe 10 or 12 billion dollars. If you look at the history of ARM, where was ARM after 5 years of commercialization? Was it worth $10 billion? No, I don't think so. So I think investors, at least on paper, have some valuation. Now, the third group of people are people who are using the IP. For them, it is indifferent. They use ARM or they use RISC-V. As long as they make good product which can sell in the marketplace, they will make money. So I think the way I see it, all three constituents are making money today. They can make much more money, but because of innovation, collaboration, and this constant pressure to innovate over a long period of time, RISC-V will do better than any closed source IP.
Yep. Thanks, Naveed. Yeah, go ahead.
Yeah, so he just said something really interesting. So we created something of value that people want, that we can sell them, but now it's theirs, right? So if we want to sell them something new, it better have more value. We've created,
Yeah.
a friend of mine said one time, you run fastest when you're both running towards something and away from something. So RISC-V has given us a requirement to continue to improve in a real way. We can't sit on it. That's all right.
Yeah, no, so I'd like to round it off. And how many RISC-V entrepreneurs or people working for RISC-V connected startups in this audience? Okay, quite a few.
I noticed like everybody from Intel raised their hand.
Right. So here is the way I answered the question, right, when somebody asked it yesterday, right? So see, today, just in silicon, there is over $1 trillion market cap if you combine the valuation of the top silicon companies, okay? That's all yours to take. Naveed just said adding up the current startup valuations is at like $10 billion, right? Like in the stuff. So there is an extraordinary, range to get to over $1 trillion. And, with inflation adjusted, by the time we hit the 2028 mark that Naveed was talking about, it could be $2 trillion available to you all. So some of the hands raised in this audience, take pictures with them because some of them will be billionaires, right, by the time this whole thing is done, right, if you do the multiples, right? So that's really the opportunity. There is over $1 trillion available for you all to take.
That's great.
Fantastic.
You have a question?
I would have a question or two. I think the RISC-V is a baby. It's a small baby now that has many family, many people who loved. But we need to grow up the baby. Okay, it's not just producing more chips. It's that defining, agreeing on the new instruction set architecture, new instruction. So how you see the future? Are we going correctly in the way we define new instruction? Should we collaborate more? How we should do that? And in the same question, how you see the influence of RISC-V in the supercomputer of the near future?
My experience and watching also some of the talks yesterday, I was very optimistic. See, the thing for this community to nail is the verification infrastructure. Okay, so if we all have agreed on a solid verification infrastructure and that we share our test vectors, everything we put there, that gives us the ability to make changes, right? So it's basically, if you have real solid, strong verification infrastructure, I can be a lot more bolder of, let me try this, let me try that to solve the problems. Like, say, I want to build a better AI computer, like, faster, reduce the TCO, I have an in-memory computing idea that I want to go exercise within the RISC-V platform. There's so many fantastic ideas. So today, if the bar of change is, oh my God, I need to do 3-year verification, what am I going to break and all, right? That's what constrains us, at least in the big companies that I've been part of. It is like the fear of change. Oh my God, you're, touching this, touching that, and that will be like a 4-year verification. Oh, don't touch it, right? So that kind of impedes innovation. So verification is enabler for innovation, right? So really strong verification infrastructure will make us all bold. So that's what I would really encourage and also do my part to contributing to the verification infrastructure.
Raja, I would like to second you, and I'll say this is a big difference between academia and industry. And I interface with, and I used to be a professor myself. Most people in academia thought writing RTL is a big deal. Actually, many professors still think that if you can write RTL, that's a great thing, and they write tools for accelerating RTL and things like that. If you talk to anybody in the industry like you and many others, like me and others, we would say RTL is great. We can write RTL, no problem. How can we verify this? In other words, industry feels, just like you said, verification is a much bigger problem than writing the RTL, the first part of it, right? So as a result, if you look at the earlier innovation in RISC-V, were writing high-level description, code generators, and things like that. They were great. Problem is the code they create makes verification even harder, right? And I think this is where a major correction needs to happen, that we should focus more on sharing verification, just like you said, building more verification infrastructure. Because if we keep on adding instruction, more complexity, we will find ourselves same as ARM or x86 in about 5 to 7 or 10 years. Verification nightmare will slow down collaboration, slow down innovation. So I would encourage the entire RISC-V community to pay 3x importance on verification and 1x importance on new instructions and writing high-level description to generate RTL code faster. So I completely agree with you. Sharing, building infrastructure for verification is the next big thing that RISC-V must do.
Okay, so I'm going to split my answer because partly we also think the verification environment's cool, and then the surprise to me was we started a new processor project, and I've done that several times at startups and big companies. And one of the first things we did PowerPC at PA Semi, we did MIPS at SciBite. We had to go build our own stuff, right? Like from scratch, reference model, test generator. With RISC-V, the reference models were great. We hired one of the guys that supports it. We then open sourced trace generation, vector extension on top of that. We open sourced a vector unit, a small vector unit, which we put on the boom core, I think. So that was interesting that it already existed. And since multiple people in different companies are using it, if it doesn't work for somebody, somebody tells somebody, right? Yeah. And so there's the power of open source, which is you can start with an elevated platform that multiple people are using, right? But the other piece is the innovation in the next 10 years is going to blow our minds, right? And I've said this before in some forums, and I'm talking to people about it. We're going to use AI to write all the code. People are starting to see that. ChatGPT, if you want to write simple programs, you use AI, right? Now, today it writes Python code or C code, right? Pretty soon it's going to write assembly, right? And then we're also going to use it to write our test verification suites, right? And that's going to let us build a processor that runs differently, right? And that loop also needs to be pretty collaborative, right? And the people who are stuck in the old idea of instruction sets narrow, verification is rigid, committees approve, changing bit 31 about the function on step 17, that is not going to work, right? So you said something that's really interesting. We've tried to build BlueSpec and multiple new languages, but we all get stuck on Verilog, which we all agree is bad, but it's like the thing that works, right? Now we're going to start to generate programs, RTL, verification with AI, which is 3 levels of, 10 levels above Verilog description, and who knows how many levels different from a spec that was printed on paper that somebody approved in a committee, right? So how do we live in a world of rapid change and new tools and new abstractions? And the answer is something like collaboration, and open source here is going to win. This is going to take 1,000 people doing 1,000 experiments, and stuff that works better will be evolutionarily selected for, and stuff that doesn't work or nobody cares about or it's too hard to use will be down selected. And that's like the difference between 20 to 100 people designing new processors, tools, and stuff versus 3 companies controlling a spec where nobody can change it. It's such an amazing difference. But I think as we start to bring AI into every part of how we do design, it's going to accelerate the change process, which is both daunting and hopeful.
Yeah, and I outside we were talking. I mentioned to someone that today an AI computer that can drive your car pretty well costs you $20,000. Okay, $20,000 to put together. Okay, this is just the silicon portion I'm talking about.
Except at Tesla, where we build a better solution for less.
Right, but not everyone. So there are how many, I forget how many millions of cars and autonomous things that we would need across the world. It has to come down to $200, right? So there is a factor of 100x innovation opportunity there, right? And some have shown it's not physics problem. As Jim said, it's not a physics problem why it is $20,000. It's an entire margin stacking problem, business model problem, and lack of innovation. It's just, hey, I'm focused on this particular problem, whereas your SoC has a million features that I don't care about, right? I just need a good CPU, a good matrix multiply engine, right? A decent memory system, and I don't need the rest of garbage that sits on this SoC. You can't get that. When you buy the merchant silicon, you get a lot of stuff, right? So that ability to just build a computer that I need for my purpose at the cost structure that I can put in millions of vehicles, right? Just using that as an example, right? That's the kind of innovation opportunity that we're trying to drive with the RISC-V ecosystem.
Raja, I can tell you one thing that at Rapid Silicon, we tried using large language models and ChatGPT, a platform that allows you to take FPGA fabric, put a knock on it, and then you can select the IPs that you can want to hang off of the knock. And we could put together something like that in a few days. It's simple, but I think these are the kind of things in future people will be put platforms like that, which AI models could manipulate very, very quickly because it's a very specific domain on which the AI is operating. You know, you're talking about 30 IPs and a fabric and some RTL thrown in. So very exciting times. I think RISC-V will play very well with AI. The reason for that is you need completely open architecture to play with AI and to play all these games. So I think AI may provide equal opportunity to RISC-V compared to ARM and the other architectures, which are not open.
Are we opening up for?
Yep. We've already got one, so let me hand the mic over.
What's the plan for backward compatibility? Everybody adds an instruction. 10 years later, you have a gazillion instructions. The new startup coming up has to now back validate all of these instructions they don't even care about.
So the question is, what's the plan for backward compatibility? There was a movie a long time ago, and there was a famous quote. It said, "The first rule of Italian driving, what's behind you is not important." And he ripped his rear view mirror off. So
I like it.
I think that's really interesting. So I believe in creative tension. Creative tension says, I need to innovate and change things to go as fast as possible. I need to build a stable platform so a lot of software and stuff works. One thing that's really powerful is building a really good virtualization method and exception method. So if you hit an old instruction, we need to coordinate stuff. Don't reuse an opcode. Change the definition so the program silently does the wrong thing, right? We need to have some rigor on stuff that's missing. Like, there's methods for doing this that are pretty good. And software, whenever you load stuff, needs to look at the hardware and say, what do I got? Like, RISC computers are cool because you know where all the instructions are. You can actually edit them really fast. You can go find missing instructions and jump out to emulation routines. And there's a couple levels of software technology that make this better. But I believe in innovation, and I want to build the structures that let us be backward compatible without requiring us to build the silicon that Raja just pointed out is a waste of time, money, and brain cells.
Yeah. So, I divide the world now as two camps, right? The world that still fully embraced the power of open source software that has happened for the last decade and a half. Okay. So you can recompile. Okay. You can recompile. Okay, so that covers, gives you a ton of freedom to innovate. And I'm, very kind of software first person. I don't like breaking a workload. Okay, I don't like breaking a workload, and which goes back to the verification discussion that we had. I think we can innovate on instructions without breaking the existing workloads, right? That's a good constraint to put on architects. Now, when you break the workload, you put the bar very high, right? Saying that, oh yeah, everyone in the ecosystem needs to recompile or something. But those should be rare occasions where you actually break the compatibility, and you should have a good reason. The worst thing is inadvertently breaking the compatibility. You didn't know you were breaking it. Okay, you thought you did something cool, and you broke a bunch of stuff. That's why the verification stuff is important, where people don't end up breaking some compatibility without even knowing they did it.
Next.
Yeah, so yesterday we were discussing about chiplets and IP. So what are the challenges when we are coming up with chiplets? Because ARM or Synopsys or Cadence, right? I don't know whether they tried or not, right? So what will be the challenges or what will be the advantages with that approach for
Yeah,
any of you? Yeah.
I have the most PTSD on chiplets, right? In the stuff I probably, if when I write my book, there'll be a full section on chiplets and all the scars, on chiplets. So there is a lot that we learned, that I learned since 2013. I've been pushing the envelope on chiplets and 2.5D integration, 3D integration, and all that stuff. So one of the first things that, when I started talking to Jim about, getting engaged on the ecosystem, is exactly the first thing we were talking is, hey, how do we make this chiplet thing? It's on a pretty hype cycle right now. That's like, and everybody says, chiplets solves all problems and all, and I just look at it and say, no, 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 right? So I think the promise of the chiplets and what they bring to the table is very clear to lots of people. But on how we do it, how we get the UCIe to actually kind of to a place where it really solves all the problems that we learned. It was hard enough for me doing chiplets inside where all the teams worked for me to coordinate the chiplet stuff, right? So, it'll be an interesting challenge to do that, across asynchronous teams going. So the collaboration aspect, co-architecting these things is very, very important. So Jim and I have been, this is a thing that, we definitely are stewing on. And, I can talk for hours on various challenges, whether it's like power delivery to bandwidth to overhead on a chiplet to, area costs and power, there's so many things, security things, how do you trust and all. So I'll pass it to Jim on.
Yeah, so the first time I talked to Raj about this, well, not the first time, but in the last 6 months, I said, we need to do chiplets, and we're going to do this and this and this and solve all the problems. And he was like, Jim, I've been working on this for 10 years. None of that will work. But I said, we have to do it. I can't build another product where I have to pay millions of dollars for multiple IPs where my value add is -0, right? I want to build an innovative AI solution. Why am I rebuilding a security platform that's been done 10 times? Why am I buying yet another network processor and gluing together 5 pieces of IP and then writing the mysteriously missing piece of IP that nobody seems to have to generate something that's already shipping in 50 products, right? And then you look at the tape-off costs, right? Like we have to, so here's the cool thing. When you have a problem, you understand it, and you have to solve it or you'll die, then you get motivated to do it. And then there's, unfortunately, in the short run, so IP in this world is pretty good, but everybody who's built chips knows you buy 5 IPs, they're all really good, but when you integrate them into a single chip, you have to do a little creative stuff. You know that this IP needs a special clock insertion. This one doesn't work with test. This one, the AXI bus needs an extra register slice because its timing doesn't work, right? To make your chip work, SoC people use high quality IP, but they're also knowledgeable enough to go figure out how to fix it to put it together, right? If you buy a chiplet, who's fixing it? Nobody. You had to co-simulate before it. So now we have a legal hurdle, which is how do we collaborate across 5 companies to build products that work? Because the specifications don't cover enough detail. So we're in a funny spot. We have to do it. It's hard. As Raja said, after 10 years of scars, there's unsolved problems. And that's why I'm going to personally work with a number of companies and figure out a way to co-simulate this stuff. And the first couple things, we're literally going to have to start taping out things together, possibly on the same shuttle, possibly have some co-paid for like the emulator. I think there's a path for a few things to open source some IP that helps the chiplets work together. We talked, but imagine being able to build an HP supercomputer where some of the components you could buy and you knew they were great, right? You want?
Yeah, we are in this direction. I mean, as you know, we would like the next supercomputer at VSC incorporating hardware based on RISC-V developed in Europe. So we have plenty of work to do, but I agree with you that we could devote our time to some part of the hardware and using the rest of the hardware that somebody else already did. So this is a unique opportunity for us. Okay. So, but coming back to some question, because I agree with you. Even I am not from a company. So we have a given number of instructions now. How you think that the instruction will grow? Who is going to decide that? Are we going to the right speed? Are we going to grow as Intel did? I remember when 30 years ago I proposed to change, adding instruction. People told me, if you don't convince Intel, you will be not able, even you demonstrate that. So how you see that this important thing will evolve? Because they are very important. This is our baby. How we are going to take it? Are we going to the right speed to do that? Should we customize from the current situation? We do that in the supercomputer. We are adding instruction to the vector, to the, how you see that in the future? I don't know.
So adding instructions or the problems you raise, Mateo, the beauty of the ecosystem now that you have access to, you can do it and demonstrate already, right? A small team can actually build it, and you can have stuff running and actually doing it that it works before even you get to the consortium, right? Whereas with Intel or the stuff, you do this theoretical modeling and simulation and all, but until you don't really have an implementation with those changes, right? You need Intel to collaborate with you to make those changes to prove that the idea works, right? Whereas in the RISC-V ecosystem, I don't need to wait for anybody to actually go implement my idea, right? And if I want it part of the standard spec, and I have a credible demonstration that it already works, and with the software and all that's checked in, the chances of even a committee, if it is I don't know actually how the RISC-V committee works and all, right? So I let Naveed and Jim speak about it. But if I am sitting in the committee, if I see a working implementation of something and that it's validated, right? I'd say, yeah, let's put it in.
Yeah, and I think another good things from the RISC-V in this direction is that at least some work we did in Barcelona is that it's not that you just add instruction, you change the hardware in order to do co-design.
Yeah.
So one thing we were unable to do at the university level, you can do that. You can have this instruction, but this instruction needs this extra hardware, and you can see the influence if you have this instruction, how the performance will go on. For example, in a supercomputing center, we have a big problem when we deal with the sparse computation. The computer now are very bad. So this is a very good topic for us to work on it, and then to be in touch with the companies to say, oh, we have this idea. What do you think? Are you going to incorporate that?
Yeah.
And
By the way, one of my dream projects with Mateo was that he builds the exascale supercomputer, and we use that to actually simulate the entire platform. So I can actually run my next architecture in real time on his exascale supercomputer.
This is a good idea.
Yeah. So that all this, even the ideas that we're saying, we change something, and even before I turn it into silicon to test it, that I have the world's largest supercomputer as my simulator for running my AI workload or graphics workload or whatever it is, right? Simulation on a simulator, right? So the reason for building exascale computers is so that we can simulate, our chips in real time in full stuff, and that's one of my dream projects for to work with Mateo on and use one of his supercomputers.
We're gonna get one more question in
So
here.
one last question on.
Can I make a comment on the new instruction?
Okay.
So my comment about that is, When somebody asked me when we were evangelizing RISC-V around the world, why are we evangelizing in Dubai, Australia, Chile, South Africa? My point was all the people who have innovated in architecture, who live in Silicon Valley or Boston or Bangalore, have already innovated. The new innovation is going to come from some weird corner of the world that we have never thought about, and we will have no idea what freaking instruction new come, and it will come from people who have no connection with us. We need to bring them in. This is the reason I did all these seminars around the world, because when people ask me, has silicon reached its potential? I said, how can silicon reach its potential when less than 0.0001% people have contributed? Let's take the percentage up to 0.1% of the world population, then it will explode. That is why I want India, China, and big population centers of the world to contribute to RISC-V, because I know new ideas will come which I have never heard of, you have never heard of, and Jim, despite his background, has never heard of, and Raja, because of your background, have never heard of. And that is the promise of RISC-V. And I welcome that promise, because that is what is going to make this whole thing exciting.
Naveed's definitely going to win this roundtable. All right, one last question.
So, so one last question on, again, chiplets and heterogeneous integration. So I just wanted to ask on advanced packaging for chiplets. So are we going to leave it for the foundry to innovate in that area, or again, startup has to collaborate with the foundries to innovate in that area as well? So advanced packaging is turning out to be a big deal for chiplets. So what is your take on it? This is for Jim Keller and Raja Koduri.
No, so I'll start. Actually, we were talking just this morning too, right? So first, advanced packaging innovation in the open ecosystem, right? That has begun, right? And we will be encouraging, both Jim and I will be encouraging startups in that area, and we'll be working with them, right? And particularly in India, right? I would love to see a healthy advanced packaging ecosystem. And I know there are some already, started off activities building in packaging fabs, packaging factories in India. But we also need the package design ecosystem, right? And they are experts, okay? They're the people who have built my most advanced packages at my last company are here in India, okay? So they know, India knows, yeah. So there is Suresh, he's in the audience right there. So I think, the advanced packaging ecosystem out in the open has to happen. You'll see, a ton of activity over the next, 12 to 24 months on that stuff. But
Yeah, so packaging's a really interesting thing. So high-end packaging people love to show me technology that is so cool, and it's taking me almost 20 years to figure out. Most of it will never happen. Like, I've been in so many presentations. We got die stacking, half die stacking, triple die stacking. We got fine pitch, 22 layer. And I think that would be so cool. And now I kind of think that'll never happen. Oh shit, that'll never happen, right? And there's a reason for it. So high volume consumer packaging where they really figure out how to nail, like, you can look at 3 packages and it's not obvious to an engineer which one of those would be manufacturable, reliable, at low cost and high volume. And then when they commit to it, they spend a lot of capital, and then they want to run that capital to the ground, right? The reason GPU packages are cheap, like they're literally cheap. You look at a GPU package and an HBM package, and one of them is $35 and one of them is $3,000. And the reason is one of them has unbelievable amount of engineering in it, and then a lot of capital spent to lower the cost, right? So we're talking about multi-chip packages for chiplets, and they're talking about a roadmap from 130 micron to 50 micron. I got to tell you, a micron, when you're sitting on a nanometer, look, it's so big, it's unbelievable. And you need 100 of them. right? So this is a place ripe for innovation, but it has to be done by people who, at the end of the day, know they have to take it from a great cool package concept to something that's manufacturable in high volume without requiring $1 billion for the capex, right? So it's a technical problem, but it's also a business problem, and then it's a collaboration problem. And again, this is one of those things, it has to be solved. I can't have 100 startups in India all looking at a $20 million bill for a 3 nanometer tape out that requires PHYs and a whole bunch of stuff, right? That's crazy, right? They want to be able to build a chip for a couple $1 million and go into volume, which means they need chiplets, which means they need a package that works, which means they can't blow half their area because the pitch of the package is so big that the PHYs are big. Like, it's such a crazy stack, but it has to be solved. But it also has to be solved by realistic people who know how hard this is, and not by guys like me who've been me 5 or 10 years ago after so many cool package things, and I think, oh, that's going to happen, and then none of it happened, or it only happened at a cost that's out of everybody's reach. And it's going to be a wild ride, but we're going to do it. I think we're going out of time here.
Yeah, we do need to move on. I was just thinking, if we did this in the US, we could have had this at the San Jose Conference Center, charged $50 a person and sold it out.
And we're going to do that next time.
So this is a really special moment, guys, and I don't think that thought is lost on any of us. So thank you so much for being here and for coming up on stage to us.
Thank you.
And also, thanks, Naveed, for dialing in. It was great to have you.
We need to move these chairs off.
Thank you, Naveed.
So, Mateo, you want to stay on stage?
Yes.
Jean, Tenstorrent, Bridget, Raja, all of you. So it's my pleasure to be here. It's my second time in India. I was teaching. I was distinguished professor from AC, and I was in Delhi and Pilani many years ago. And at that time, the RISC-V was not the reality, okay? And what happened that I think that one important thing for RISC-V for India also, if I can say that, is that many talented people can stay in his country doing things. And because when I came here, many people, I met many Indians researchers in the States or in Europe, but not here. So I would like to thanks to Tenstorrent to install and many other the company here, because that allow the people to decide they like to stay in his country, move, and not be forced to move. And I would like the same happen in Barcelona. We have a more difficult task to do, because this is the way to copy you and then to produce, to educate talented people as Mikel, who attract talented people from outside and retain our talent. That is very important, okay? So I was thinking, I am a very old man, so I had been 49 years professor. I am not so young. Okay, so I would like to say something about the Barcelona Supercomputing Center, how we did with RISC-V, And if you allow me, just the origin for that, okay? So, is there? Sorry, is that worse? Okay, so this is the Barcelona Supercomputing Center, is the Spanish National Lab. The most important thing is there's a collaboration between institutions. The Spanish government, you know, we have different regions, the Catalan government, the capital. So, in a church, we got all the awards. It is the most beautiful place, so I invite you, when you can in June, to the RISC-V Summit. I would like to invite you to visit the church. Okay, I was the dean many years ago when the church was desacralized, and we used for that. This is a beautiful Barcelona, probably for me, one of the most beautiful cities in the world, for the culture, the way people, I mean, for many things, okay, and the food. So, and this is the Sagrada Familia, obviously. What happened? Sorry. On the right, the Sagrada Familia, it's almost finished. I invite you to go there. It's an incredible cathedral. And then, this is the UPC. The origin of BSc is that at UPC, my university, you have some numbers there. I will pass quickly. You will get information. So when I moved there, I am telecommunication engineer, but I moved to computer architecture after I meeting a professor who came from Stanford. Unfortunately, he passed away. We are what we are in Barcelona because Professor Thomas Land was with me. I was his student. He left. I was alone. And then I say, what I should do? Should I move to UCLA with this guy or I stay there? And then I start creating the computer architecture department many years ago. Okay, so I start having students, more student, professor. I was the only professor now, and now there are more than 100 professors in computer architecture. So we start collaboration with companies. I think that we can produce paper for ISCA, micro, SPC, whatever, and at the same time to work with companies, because the idea should be be used by the companies. I don't think the target for the research should be to publish paper. It's to motivate the society to use our ideas, okay? So I have a very clear thing when I was very young to contact Intel. I got a PhD student, to IBM, and then one of the things I did was to establish a center on parallel computer after basic research, okay? So I start my research in the 80s. Before that, I did worse. I was the advisor for 3 theses in systolic array processor, and now I realize that almost all the accelerator are matrix by matrix. We did that many years ago. We do different things. So we did. So one thing we did is to believe in vector architecture. Nobody believed in vector architecture, but at that time, the micro killer convinced the people to say, no, not anymore vector architecture because the superscalar will conquer the world. And I say, no, it will be the opposite. The vector architecture will conquer the world. And when you see the current high-performance computer, all of them are vector architecture. Short vector, long vector. The GPUs are vector architecture, okay? So even sometimes we confuse GPUs with vector architecture, especially some people, okay? So I did the work in vector architecture and continue. I think that a very good idea was to say the scalar processors are advancing, the vector architecture are in the old state. Why we don't put both things together and we put instruction level parallelism and data level parallelism together? Okay, so I had many theses on that topic, and then thread level parallelism, many multi-core. Okay, very interesting work. So my students were working in all the different kind of architecture. It was a very good thing, okay? So I think we have a pioneer influence track war in vector architecture. By the way, Christian Naveed, who was invited by me 30 years ago in Barcelona, started the vector architecture start after us. The advantage of this guy is he was able to tape out. We were unable to tape out, okay, just ideas. So I had many students, publication. The family is 1,000 people. I had a very huge family of PhD, and every week I think we have a new baby in the family. Okay, this explosion. So I am very proud of these guys. And then okay. So this is Miquel Moretois here. This is okay. So from I prepared this slide when I was 70 in July. I by 140 people worldwide. Okay, but just Miquel passed from 9 to 12 PhD student already. So the family is growing. Thank you, Miquel. Thank you to all of you. So we start as a computer architect building our board. So this is the first one, terrible. But let me tell you the one on the right one, who's very, at that time was very important, was in 98. So here you have for Intel 386, we build a gate arrays, share memory, and we put these two processors at the transputer in order to execute high-level operation in the memory and the I/O. So it was many years ago, and I am very proud of my student who did that at that time. Okay, and then I start in '84 a center doing with parallel computers. Okay, and based on this board, I mean, we were acquiring mainly the transputer processor. It was European processor, and then we had plenty of different machines. You can realize the Stigwala convex machine. The vector here is the connection machine. So this machine, 8 Qs, was the fastest supercomputer in the world for 1 year and a half. He was produced in MIT for artificial intelligence. They put floating point engine to allow to pass the test of the impact. And then until we arrived, many different machines, we were growing step by step, slowly, at the university level in order 20 years later to convince the same partners to grow up to be the Spanish National Lab, the Barcelona Supercomputing Center, okay? So these are the picture of the December 31. Let me tell you that we are now 825 people, we are growing. And you can see that we had 4 departments, as Miquel said yesterday. So we had almost 700 people. We had 700 people doing research in 4 topics: computer science, life science, earth science, and engineering, okay? And the important thing, I am very proud of that, 40% of our people comes from 54 countries. So it's a national, and okay. So this is the way we grow, and then these are the prediction because we had plenty of open position, okay? Especially in AI, especially in chip design, in climate change, life science, okay? So these are the 4 departments. As I mentioned, you will get a slide. So in computer science, this is the picture at the end of the December. So you have here the topics, the main topics. We have a huge computer science department, almost 300 people. Okay, so we had, since many years, we had plenty of experience from the application to the last bit of the hardware, okay, with all the layers of software. So, I mean, for example, the performance analysis tool we started 30 years ago, probably these are one of the best ones, giving you information about the behavior of any program, any architecture, blah, blah, blah. So we introduced 5 years ago the idea of why we don't build hardware, even we are a research place, okay? And one important thing is that we had people from 30 different skills. So this is a place where we have computer science department, 3 vertical. We are working together, optimizing anything. It's a very good environment, okay? So life science, the main topic for life science is digital twin for the human body, personalized medicine. They are working with many hospitals, many research centers. So we are a very big family, okay? And they are using artificial intelligence simulation. They are using what you can imagine. So we had many different topics. I invite you to go to the website, Earth Science. The main topic is climate change. Quality of the air, simulating. Okay, we are using artificial intelligence to simulate, to predict the quality of the air of the cities, as Mexico, Barcelona, many other ones. Okay, so the same, and we have a very strong department on engineering. Okay, any kind of engineering. So I will provide you with the slide. I mean, Tanuja will get and please put public. Okay. So and these are as I say, multifunctional. We developed from the scratch huge software as ALIA, for example, is multiphysic, and then we do simulation, real simulation of the heart, of the respiratory. I mean, many people, many talented people from 54 countries. I am very proud of being one more in this family. Okay, fully connected. I think one of the things RISC-V allow us is to naturally collaborate from the university level to the companies worldwide. So I would like, obviously, the circle from India to grow up, okay, to establish more collaboration with India. We publish plenty of paper. As I say, our lemma is our research is excellent. We publish Nature, Science, ISCA, but mainly relevant. We need to produce ideas that can be used for the society, for the companies to bring these ideas to the market, okay? Okay, we work with many companies. Intel was the first one, IBM was the first one, NT8, I was in Watson. So, I mean, okay, so many, so the idea is that we define common topics and then we work on these topics, okay? Okay, so let's go to Europe and the SPC very quickly. Mikel saw that. I say that in the panel. So it was even worse before the Linux. But Linux produced this blue color in all these levels, okay? And that will allow people to collaborate. But when we arrive here, Houston, we have a problem. We cannot bring our ideas to the hardware because you need to convince Intel, NVIDIA, whatever, so you are killed. So you need to wait until the companies produce the hardware and then you adapt your software to the hardware. And this is what. And I think that happened with NVIDIA. Jensen should pay for the rest of the world the million of hours we spend adapting our algorithms to the GPUs. And probably this is not the right way to implement the algorithms. Okay, many of the algorithms, we change the algorithm in order to adapt to the hardware. Okay, but this is my idea. And I told that to Jensen many times. So when that happened, we in Europe, the BSC, thought that Europe should develop processor in Europe. The only one, or the only opportunity we had was the R. Okay, as you know, start by small things, growing up slowly, 40 years. By the way, I arrived late. Spain was invited to be part of the European Union in '86. I arrived late when the consortium was already formed. It was and Steve Farrell, Mateo, next one. In the next project will be there. I was not in the next one because it was so successful that they didn't need any university person, okay? So we did that and we start developing software for the R, predicting that in 10 years, the R should be so good that the processor will compete against any other processor in the world. In fact, 15 years ago, I was with the CTO in Cambridge, proposing him why we don't build together an R vector architecture. He said, too early, but we will go in this direction, 15 years ago. So we did that and we produced several, and then we built two rackets with chips coming from the Samsung Galaxy 4. Okay, the processors were R with the Mali GPUs, and the idea was just to develop software, waiting for the king, waiting for the good hardware to go there. And we were very happy because we say, the R speed of the process is going up, so we are going to have the first European supercomputer center with European hardware, okay? You know, so we did that, R, we built that, but suddenly the color changed from blue to red, and then it was from the Japanese, and they took some of our ideas. We were collaborating with Riken and Fujitsu, and then we are still collaborating with Riken and Fujitsu, and they produced the Fugaku, who was #1. And I say again, Houston, Europe has a serious problem. We are not going to have any more supercomputer with European hardware, okay? But God is good. Good. When you think that you are almost killed, the light appear and you say, move up and go up. Okay, so this is the real situation in Europe. Okay. Let me tell you that this is the chip, the board, and the color was put by Atos. I don't think this is true. but I mean, to be serious, to be technical, but it's almost represent. And you see, the red color is bad in this case, okay? So we don't have CPU. This is for HPC, okay? We had some kind of accelerator, neuromorphic. We had very good neuromorphic competing with the true north of the state, with Steve Farber, with R. But now England is not the European Union, so we don't have. Okay, the quantum we are, I think even, I think Europe is going in the right direction, but I am not fans of the quantum computer. I would like to touch real things, but I mean, okay. So this is the situation, okay? And then I was predicating. I am a little professor, predicator, priest. I mean, many things. I need to do many things. So I was say, listen, we need to do some effort in Europe. We cannot be maintaining just buying computer, using them. We need to produce something, okay? Okay, at the beginning with R, so when I received the Seymour Cray Award in Austin, I say publicly, we would like, and then we changed the mind, and then in Europe 5 years ago, we established what we call the European HPC, high performance computing. It was 6 countries. We proposed that, Spain proposed that. We signed the initial contract agreement in Roma, and now all the European countries are there, okay, and some extra countries, for example, Turkey or another one is an open organization that you can join. So with 2 targets. The first one, Europe needs to get access to the best supercomputer because they are necessary for producing good science and good things for the companies. But the second one, I am more interested, I push for that. We should try to do something, even it's very difficult, it's a very big challenge. Probably we will not get that. But if we don't start, we will never reach. Even not to the final that we would like to have, but we will do something, okay, to produce technology, okay? So that needs money. So for the first target, Europe invests money. So what Europe say, okay, the supercomputers are so expensive that it's very difficult for the countries to buy their computer. Let's go to pay half. And then let's allow to the countries to join effort, to co-participate in buying the machine, to be co-owners, okay? So we did that. Okay, so you had you need to multiply by 2 because this is the money European Commission put, but the countries need to match the money, okay? So it's a reasonable amount of money. And now you can see that there are 3 pre-scale machines, one of them in Barcelona, we are installing, this is Mannerstrom 5, and then some petascale, and then the first exascale will be located in 1 year, 2 years in Jülich in Germany, and the second one in France. So the first objective is very easy. If you have money, you can buy the supercomputing you like, okay? It's very easy to get. It's very simple. The second one is more difficult. And then in these first things, let me tell you, this is a new, we are going to install the Mannerstrom. We have the storage now, and the first Sapphire Rapids are coming, okay? So we are going to have we don't believe in the lean pack in the top 500 because with the money we have we could be now number 3. Okay, if you buy petaflops with NVIDIA, the cost is 3 petaflops, 1 million euros. We spent 220 million euros in the Mannerstrom 5 with the electricity. But we are a research center, so we would like to have different kind of machine. Obviously, the Rialto will not be a reality, so we are going to change that probably for a RISC-based prototype, okay? But the good thing, I would like to emphasize one thing when we are talking about NVIDIA, that even in the Limpac, which are very simple things, they are getting 60 to 63% of the efficiency. But when you go to the conjugate gradient dealing with the spark matrices, they are getting 2% of the peak performance, okay? We can talk about it, we need to be, but this is the reality, okay? So, okay, so because the new way with the RISC-V is democratizing hardware and software, is creating a new environment to collaborate, to co-design. We created 3 years ago in November, I think 3 years or almost 3 years in the past November, we introduced before the pandemic in the state, what we call the LOCA, Laboratory for Open Computer Architecture, is just to work on this new picture where we can collaborate. The important word is to collaborate, okay? And we create that because we think that BSC is one of the places when we can deal from the application to the last bit of the architecture. We can do co-design. We can know everything about the application. We can predict what the application the future will be because we have people developing software, huge programs, big programs. So we had plenty of experience. I can tell you that we did the co-design with IBM with the cell processor, okay, and we were working for the next one when Sony decided to buy AMD. Okay, we were with Peter Hosty. We were working in the memory hierarchy BSC. Okay, so we did co-design. We did supercomputer devoted to run RTN for the Spanish petrol company, who we produce one of the best software to tell them what they drill in wild ambience as the Gulf of Mexico. You don't know what to drill. One every 10 trials success. It's very costly. So I mean, we create this environment and we are trying to do things, okay, the idea, okay. So it's an instrument to allow collaboration. Obviously, I would like to have Jean, Brigitte, I mean, many of you, Raya, to come there and to teach to the student. Just 1 hour of these guys could be incredible to motivate all the people who really design processor, okay? So we would like people with experience to spend 1 week with us, 2 weeks, and some of them did that. For example, Steve Wallach, the guy who did Convex, and many others. Arvin, we had many people. Okay, so this is the idea. This is the human tower we built in Catalonia, in Barcelona. So this is the idea that together we can go up. Okay, this is the idea of the RISC-V. Okay, for me, together we can move farther away. Okay, so we did that, and the important thing, one of the important things for me as a professor, RISC-V allowed to change the way we teach. And this is very important. So we create, based on BSc, an alliance at the Spanish level. Probably that was sent to me yesterday night, so I don't know what that say. But okay. So the idea we have connected all the universities. We would like to produce some Raspberry Pi based on RISC-V, and then to transfer this idea to Europe worldwide. Somebody else do that. For us, it's okay. We will, because I mean, it's a new time for the different universities. I don't know, in this core or this load store queue or this the buffer renaming, whatever. Okay. So I am very happy about that. I am not happy about my age. I would like to have 40 years at Miquel to put all my energy in all these things. Okay, there are many universities and many others in Spain. Okay, and what we say, and this is very difficult, especially for companies, that we coined this 3B for HPC. Barcelona build versus buy for HPC, for high performance computing. We like to devote our effort in RISC-V HPC. Okay. Again, so based on that, what we did is the opposite. Even companies, it was, now that is changing. Now European companies appear at Codaship, Accelera, Semidynamic, Cortus. Okay, the field is growing in Europe, so I am very happy about that. But we convinced to the guys from IoT, it's another division, the European Commission say, listen, Europe need to decide that the future is just RISC-V. And we did that. I was very happy when they organized in Brussels this seminar, where it was a decision that the European Union will put money in RISC-V. Okay, it was a very important decision. Okay, so we start step by step how we get exascale machine very slowly. We know how to do a small building, but NVIDIA ended up building 200. Can we go there? Because when we arrive to 200, there will be 300 or more. Okay, so we start some project. I pushed for the EPI, European Process Initiative. So unfortunately, I was unable to convince to get the 80 million just for RISC-V. We got 20. And with 20 million, we did quite reasonable things. But the BSc start with drag at the, Miquel gave the lecture yesterday. And we have a European project at MIP, eProcessor, Europilot, SGI2, API2, and the next one where BSc is the leader, is the coordinator of this project, okay? Any project based in the previous one and going up. Some of them are devoted to build accelerator, I will show some of them. Some of them are going to build general purpose processors. The e-processor, the European processor, is a 4-way out of order European processor, okay? So we are in this direction. So if you look the future, and it was said by Jean and Raya, the future will be heterogeneous, very heterogeneous. What kind of accelerator will be in the supercomputer, we don't know. If you look the current top 500 list in the machine, plus accelerator as NVIDIA, AMD, or Intel. And you have another kind of supercomputer that I love more, is the Aurora, Japanese Aurora from NEC, who is a real vector architecture at Seymour Cray established in 75, many years ago, 50 years ago. And I think this was a very good idea, who needs some word on that, some explanations, and okay? So, I mean, these are the two kind of chips. Are we going to, I mean, what happened that my people, well, the people, I don't have people, I have a son and granddaughter, but the people who are working on application people, anytime more, they are incorporating techniques from AI, running, substituting they train a network, and they check every day if the quality of they predict in Barcelona is the sensor is the one we predict, and they change that. Or what happened is that they run in parallel let me tell you, the physical application, and they run some AI to guide, to optimize the, okay. So that should be taken by the computer architects and adding some different hardware to the one that has been during the last 15 years. This is a big challenge. On top of the neuromorphic quantum computer, I mean, I am not talking about very soon. We are going to install the first one in 2 months. So, okay, so I believe in vector architecture. I think, I'm sorry not to be humble here, that my student did the bandwidth. Many things, the command vector memory, you send the information from the vector to the memory controller instead of sending address by address. Many things. Decoupling vector architecture. Barton Smith, who passed away, told me, Mateo, after I read your paper, Cray designed the IS-1, decoupled vector architecture. We are using this concept in the chips we are building now. Out of order vector architecture, the RISC-V, the RISC-V of the supercomputer was the Cray one, was very simple idea to take advantage of the technology to have a clock of 12.95 nanosecond at that time. It was incredible. Okay, multi-thread vector architecture, simultaneous, and then NVIDIA is a multi-thread vector architecture. We produced the first paper a few years before that NVIDIA produced the real hardware. Many things. Vector, short vector, we evaluate the different vector length in the different application. Okay, we did many work. And we are continuing with the main topic for me is how any architecture deal with the sparsity who is in many of the current supercomputer application, and now in the future AI application. Okay, so we start with the API. Michael mentioned something today. I mean, it's very difficult, to be honest with you, to work with in Europe, because we are politically forced to be with many partners. And how you share things, it's very difficult. Okay, so we produce a chip where they have several, with the tape out, where we have different accelerators inside the chip connected to a general purpose processor. Okay, so we have the vector architecture here. Okay, the core and the BPU, and we have STX accelerator and variable accuracy accelerator. Okay, and we have network chips. We share anything. Okay. This is the way we work. If you like details, we are coordinating this project, okay, BSc. You can see, I mean, it's very difficult. After that, if I like to do a tape out, I need to convince to the people who work with me in the project for the IP. In fact, this is the problem we are going to have. This is the structure. I mean, believe me, I mean, it's a vector architecture. It's not a GPU. We have just a single program, okay? And then some the instructions are vector, and there is a vector part in the processor who execute. Okay, we don't have to pay this moving of data, this moving of control. It's a very simple. We compile and we run. Okay, we simplify and then we have the vector. One difference is 256, who is not new. The Aurora from NEC has vector length of 256, okay? Because we think with our simulator that is a good number, okay? And we are, by the way, executing, this is the tape out, the first tape out. Michael said we send the second one. So we are advancing, okay? And then we are now to start a new project, which is called FPA, who is taking the original status, and we would like to change at least the blue in the low layer, and then to do more application, whatever. And this is the idea of this FPA. Okay, this FPA we are preparing. BSC is the coordinator. We are having now 40 partners. It's impossible to do this. So my idea is to clusterize. I say, okay, we are together, but a little isolate. Okay, so the idea is that to bring, I mean, this is what in the state you have, how we can do the same in Europe, trying to design a GBP. We don't have the copyright for the piece, I'm sorry. So this is our idea, okay, how we pass to that, okay? And then we are going to do, we are going to improve our back accelerator, our BPU with the scalar, our vector architecture, okay? One of the things we are going to move from 16 operations per cycle to 64. But now, if you tell me, you say me, I would like 13, I will give you the 13. 15, 15. I mean, as you know, this is very easy to do. Okay, so we are going to do that. We are going to improve the STX. Even I am not very fans of this one. Okay, I don't know if we can do the same or more with the vector. Okay, and then we are going to do an AI, infinite machine, in order to be used in the future supercomputer. And we have what we call a GPP, who is a Sapphire Rapid or is an R with a very big superscalar processor plus some small Cindy machine. Because, by the way, for our back architecture, we need just 2 way out of 4, that is enough. Okay, to order, so it's very simple, the process, but for the, so this is the ecosystem. We are going to have, we are going to develop software, to continue software, pilot, we are going to do pilot. And the important thing is that the target is for the target is all the European supercomputer centers are there with their application, just to see how the application. Personally, I think that as a design, how you incorporate new feature at the architecture level, because the RISC-V doesn't say anything. The RISC-V is not a contribution to the computer architecture. It's contribution to improve the computer architecture, to improve the collaboration. And you collaborate, we will do better things. Okay. So how we improve the efficiency of the dense computation is a problem. So we have some ideas. We publish some ideas in SPCA, whatever all this conference. So this is one thing. I repeat that we can test. We can do some RTL design, FPGA, whatever, and then to add new instruction to see the cross-pollination between new instruction, new hardware, and the influence these new things have into the final performance. Okay. So this is the possible roadmap. So we have now with EPI Europilot. We have an Europilot where we are developing new chips. Okay, we have the main road is EPI 1, EPI 2, and FPA. But collateral, we have some project helping to that. Okay, so one of them is the Europilot. Another one is the 4-way superscalar processor from Cortus and BSC. So now we are going to have this one. Okay, and we are going to have 2 Europilot with the hardware we developed here. We have for accelerator, we are going to have a pilot with this accelerator, okay? 2 pilots, okay? And probably we could use the first time if we, at least we can make an alliance with Tenstorrent and advance that, for example. But if we go alone, and I wouldn't like to be alone, this is our prediction. We could have 28 some reasonable hardware accelerator with the software. It's important to have the software, because if we produce hardware with a software, nobody will use that. So there are plenty of, thank you. So this is one, okay. And then we have the same for the GPP. This is our target, okay. And then, okay, so we would like to have this scheme. I would like to advance with collaboration, these things to the left, okay, because it's too late. But if not, we will do that, and probably even alone, the European, we could do that, okay? And the most important thing is that I convinced the European Union first time to have procurement, to have flagships as the Aurora or Frontier or Fugaku. Normally in Europe, when you get the money, you go, you establish a tender and you buy the best but you didn't contribute to the hardware, to the software, whatever. That changed, so concatenate with this FPA, there is the idea of having the Mare Nostrum 6 and other European and not European computers. So obviously, talking to the money, we spent 220 million until now. We are going to spend 270 million in the FPA, okay? And then with these things, and then the Spanish government just assigned 300 million for the Mare Nostrum 6 to make that possible, okay? To see how the European technology can be bring to the future Mare Nostrum 6, okay? So, I mean, we have some prediction. The predictions are done just not to be true, okay, but at least we have, okay? So we are doing many tape out now, okay? So Mikel showed you some of them, but we have many tape outs for the vector machine with different kind of BPUs, with different kind of scalar processor, different kind of memory hierarchies, interconnection network. And we did some of them as the one I showed to you, but we had in the e-processor, scalar processor, the green one, in the Europilot, these are already existing project. EPAC is from EPI, okay? And then from the FPA, the DAR we call DAR. We will have 2 tape out there, and we are going to do more tape out. These tape out are just BSc. We have money to do this tape out, and we would like to do this tape out with Intel, okay? I would like to do this tape out with Intel, very strong. I think we can get very good performance in real application. And then we need to see how we do for the Mare Nostrum 6. So this is our roadmap for the BP, except the e-processor, but even this superscalar processor has a BPU. Okay, the e-processor, our e-processor has a 4-way plus a BPU inside. Okay, we had a BPU also, small BPU. Okay, so this is our future roadmap. Any question will be welcome. Okay, and in Europe we have the European Chip Act. Okay, with devoting a lot of 43 billion to that. Okay, I will give this information as the American Chip Act, whatever. And then the good news is that Spain is devoting 12.4 billion. I don't know what to do with this money. 12.4 billion. Please, give
Tenstorrent.
me,
Tenstorrent can take the money.
Give me. You are solving a problem I have. So, thank you. So I mean, so I contribute to the writing of this proposal. So you will see that many things are possible in RISC-V. We are potentiating not just European but Spanish level. We are doing many things. One of the main targets, it would be difficult, is to bring some foundry in Spain, but we have plenty of money to develop RISC-V chips, to do many things, and then to do, I don't know what is the education. The education, I put this thing, especially I put this money here, 80 million, for the Spanish universities to educate young people. We need the young people there, okay? So associated to this money, we create this company. OpenShift will be very active in 1 month or 2 months from now with this objective to create hardware that will be in the Mare Nostrum 6. It will be the company who will bring, I would like, European hardware to the Mare Nostrum 6, but not for the Mare Nostrum 6, to really produce. And for that, I think we need collaboration with Tenstorrent and other companies worldwide, okay? Many things, okay? First customer, we have a customer. It would to have customer, a huge customer, and many others potentially. And I would like, if I think in India you had similar projects, so it would be my pleasure to do something together at the Indian level, okay? So, okay, so ideas about that, I don't have time. You will have collaboration, advancing, slowly, big challenge, but happy to collaborate on that. So another thing, this is the president of Spain. He's quite friend of mine, I can say that. And this is Pat Gelsinger, quite friend of Brigitte and Raja and many other people are here. So they agree and establish a joint lab You know, the situation in Intel is not very good now, but he was visiting me in February, March. We are continuing with the idea of having something together, and we are going to make a tape out now as a first thing doing that, okay? We established the formalization of this collaboration in the supercomputing in Germany, okay? This is an idea that I like more, and then I would like to thank Raja and Brigitte and many others for your help on that and many other things, okay? Finalizing, hiring is important. Hiring, okay? It's very, very important. We have this thing who attract people. This is very important. I am in the, we are 6 people in Europe trying to define things about HPC. So we consider that the collaboration outside Europe is crucial, okay? Sometimes the politicians do not see that, okay? With people as Trump or these guys or many others, okay? So, be careful, Mateo. You are moving Europe to the cliff. No, I am professor. I think the science is a very, very, very good mechanism to produce peace in the world, okay? So I need to collaborate. I will continue collaborating, okay? It's in my genes, okay? So now it's a reality. We produce the first collaboration with Latin America. I create a network of supercomputer in Latin America, okay? But the next one would be with Japan. It's an open call now, 5 million. And then the next target for Europe is India. So I am very happy about that because that will allow to the politician to take the picture and then to us to collaborate, okay? So everybody in his position, okay? So I would like to come, I told my wife, next time you come with me, okay? Because I like to go to India many times in the short time from now, okay? Thank you. So we had money, we have money and we need talent and idea. I think we have ideas, but what we think is talented people and mainly people having the experience of having done that. Because we are a research center. 5 years ago, we were unable to, what is the RTL? What is, and we produce, I mean, I am very proud, Michael, of what you do. And you know me, you are your fans, okay? But we need these people to advance in collaboration worldwide, okay? So we have all these things. This is the beautiful Barcelona. Please come there. I will be waiting for you for this summit. And this is the building, okay, where we are located, and the chapel is behind that. You look at where the thank you is the chapel connected, where we had the computer. So thank you very much.
I have to say that we now know he's the most popular man in the room. I've never heard someone say I have $12.4 billion before.
And more.
And more. Woo! So in all seriousness, there's a lot of collaboration.
Don't take the.
But in all seriousness, I hope everyone understands the collaboration opportunities. There's a lot of opportunities here. There's money behind it, so please reach out. So listen.
The money is not important. The ideas and the people are important.
Listen, we're a little behind, but would you answer 2 questions before we switch?
Yeah.
Okay,
3
let's
and
do
4.
2 questions.
I will be the whole day here and
Okay.
tomorrow.
Who would like to ask the first question? And it can't be, can I have the money?
Don't ask for money, please.
No questions at all?
I am very clear teaching things. I am
Okay.
I am professor.
I think
I am
everyone.
professional.
Okay, well, thank you very much.
Thank you.
It's okay. We're gonna. Okay, one question.
Easy question, Brigitte.
Easy question.
The one I asked.
Yeah, Professor Mateo, what's the process of getting students from India to come work or study at BSc?
We had a student from India, and with very good results. You can say something. You can answer, but don't make me so happy. So it would be an honor for me because really I consider not me in Europe we consider you the most talented people in the world. Don't have any doubt, and I think it's true. All the I know. I mean many professors. I mean I can take Arvin in MIT, Uri Sohi, in Wisconsin, very good computer architects, many people, the best one. So it would be my pleasure. I wouldn't like to take people to Tenstorrent, but Barcelona is a very good city. By the way, very good food. I cannot say very good soccer because yesterday the Real Madrid beat us 4-0. I am very disappointed. But that may so I please, if you like to come there, we have people from 54 countries. We have now 100 open positions. An OpenChip will open another 100 or 150 more. I try to convince to the Spanish and European authorities. Spanish is easier. European is more difficult to establish in Barcelona some kind of design city in Europe, design city, not the Silicon Valley, design city. And Cisco was established, Qualcomm is going to be established, and NXP. I mean, so it will be an honor for me that the people who like to come to Barcelona, is a very nice city, very good food. You can walk. I spent there 49 years of my life. I arrived when I was 21, when I finished in Madrid, and I will do the same. The culture is incredible. Well, there are some people from Catalonia who are not very good, but
Thank you so much.
Thank you.
Excellent presentation. Thank you. Okay, can we have the members of the customer panel come up to the stage? I believe there should be 5 of you. Do you want to, hold on. Okay, audience, raise your hands if you would like a 10-minute break. 10-minute break it is, okay. Hey, but we'll try to keep it to 10 minutes, okay. Okay, we're going to go ahead and kick this off. This is something I've been looking forward to. It's always great to hear from the engineers about RISC-V technology, what we're doing, how we're innovating. But it's also great to get a customer standpoint. And so we're going to do that today. I'd like to introduce Keith Wittick. He is Tenstorrent's CEO. I've known Keith for more years.
COO?
Did I say CEO?
I just got a big salary increase.
I've got a big news announcement. No, I'm just kidding. He's our COO, Chief Operating Officer. My bad. And I've known Keith for way too many years, but Keith's worked at companies such as AMD, Google, Tesla. He has a long history of working with Jim. And what I love about Keith and what he brings to our company is he brings a lot of technical business expertise. And he knows how to do business deals using the technology that we all develop. So he's a perfect person to do this panel. So Keith.
Thank you, Bob.
You're up.
Thank you, Bob. Everybody can hear me, right? So what we wanted to do before I introduce the panel is, this is the second day of the conference. These conferences can be exhausting, right? There's a lot of interesting strategic discussions, people talking, solving problems. You really have to pay attention. And so I appreciate all you being here, middle of our second day. And we just wanted to just liven it up a little bit, get interpersonal. Tenstorrent wants to have fun. We work really hard, and we also realize that we have to have some fun along the way. So I wanted to share with you a personal story that really is pertinent to me being up here today, which is, I think Americans have worked really hard and put in a lot of effort the last 6 decades to get everyone on the planet to hate them. And I think that's really, really unfortunate of us. And so I, about 30 years ago, started a tradition. I said, every time I go to a country whose native language is not English, I am going to take the time and show the respect to learn that native language and do part of the introduction of my talk in their native language. I felt that was the right way to show respect for different cultures. And so I went to Shanghai, it was probably about 8 years ago, and practiced Mandarin and learned Mandarin, and went up on a stage in front of 1,500 to 2,000 people when the government was broadcasting this live on local television. And I said what I thought was, hello, my name is Keith Wittick, and I come from America. Instead, what I said was, hello, I am Keith Wittick, and I come from a delicious fruit. And what I turned this unfortunate event into a learning experience, and I learned that in Mandarin, inflection in words matter. So if you say mei gua versus mei gua, it's 2 different words. And I think, by the way, I think that's horribly unfair for English speakers because we don't do that in English. So I learned that lesson. So I was up this morning at 4 a.m. learning Hindi, and it dawned on me that sometimes you should admit you're not good at certain things and come to terms with that and stop traditions that aren't working for you. A little voice in my head said, Keith, you have to stop flying to all these countries all over the world and embarrassing yourself. So it's with deep apologies that I tell you this whole introduction is going to be conducted in very boring English. But listen very carefully. Sometimes I screw that up. So with that, I'm going to kick off this panel. Thank you all very much. And thank the panelists in advance for coming up here to talk. So I'll take Sanjay Wandhekar, Senior Director of HPC Tech, CDEC, Pune. Then we have Krishna Rao, Senior Director, CDEC, Trivandrum. Hello, sir. Thank you. We also have Upen Desai, CEO, Speedgaze Technology Solutions. Thank you. And then we have Subhra Kranti Das, Manager, R&D, Sales. Nice to meet you. All right. So we'll kick this off. Where I wanted to start, gentlemen, is HPC market. That's what we're talking about. All of you are going to be building that business here in India. What is your assessment of where HPC is in India right now? And where do you want to see it in 5 or 10 years? Let's just lay a foundation where we can start talking about RISC-V and other things, but where is it today? Where does India want to go in 5 to 10 years in your view?
Shall I start? So I'll just give background what is happening in HPC in India. So we started this journey of HPC recently in 2012-13. So we worked on the proposal of National Supercomputing Mission, which is actually building the supercomputing ecosystem within the country. So apart from that, we started another journey of RISC-V development, RISC-V processor development also during the same time. We made a proposal of building the microprocessor for India. And that is, I went to Berkeley in sometime in 2013. And that time we were actually looking for open architecture. And that is where I think we were actually finding out what are the architectures which are available, which we can utilize for our India microprocessor. So that time OpenRISC was there, Spark was there, even the IBM Open Power is also actually coming up. So these were the architectures which were contending for that. But that time we chose RISC-V as part of our proposal because we saw the basically the potential which is available and the openness which is there and what kind of innovation we can do in that. So these are the two proposals we started way back in 2013. It took little time for us to convince the government and the funding agencies to bring the actual projects on board. So this RISC-V development started way back in 2017. So my colleague is developing RISC-V processors, which are embedded class right now, and he will talk about that. Regarding the HPC development, we started our project of this National Supercomputing Mission in 2016, and we have actually developed many things in this ecosystem. We started developing these HPC systems way back in 2017, and we started with assembly of the subsystems within the country, starting from motherboards onwards and the complete software ecosystem within the country. The next step was to have the manufacturing facilities within the country where we can build these motherboards and everything within the country. So that is the next step we did. Third step was developing the motherboards and things. That is also we are done. And fourth step was basically building the processors, which are HPC class within the country. So till now, we have developed about 15 supercomputers of 24 petaflops within the country, which is phase 1 and phase 2, we call it, which is manufactured in India with the complete software ecosystems developed in India. Now, third phase is going to start, and we are developing about 9 supercomputers with our own server boards and software ecosystems and everything. So that is the state of currently, and this 9 systems of 40 petaflop will be built within next 1.5 years timeline. Now, we are also started the work on the HPC processor, which is currently ARM based, and we are looking forward to have RISC-V also in this HPC processor. So that is a timelines what we are looking for, and we are looking for RISC-V as one of the major contender for both as a general purpose CPU as well as accelerator within our next generation supercomputers.
So if anybody wants to add to that, jump in. Don't feel compelled, but we are at Tenstorrent an equal opportunity panelist. So we'll make sure all of you talk. So if there's anybody that's really quiet, and I want to warn you, jump in early, because I think this last question requires on-stage application of like linear algebra or something like that. So get your words in early. Anybody want to keep going and add to that?
I come from a very different space than he's talking about manufacturing motherboards and manufacturing supercomputers in India. So I come from media entertainment. So exactly in 2016, we used almost close to 2,000 servers every day in cloud, Amazon or Google, to render our feature films. That is where I clicked the idea that nobody is doing this in India, and we need supercomputing resources in India. And I sold my animation studio to switch to completely from a creative to a technical field, because I saw a great future in building HPC computers in India. So we have our cloud in Mumbai now, our own private cloud, which serves to media entertainment facilities for the rendering and simulation to make films like if you see Tarzan or Jungle Book, where entire environment is built in computers. So it's a completely different kind of space, extremely complex things to do. Even a small leaf that is getting wind is simulated on computers. Yeah, so that's the kind of work we do, and demand is just going to explode, I think, in the next 4 or 5 years, because the content. If I just look at my industry, then content is going crazy. Like you have OTT platforms, mobile platforms where content is created, and all of them are going to require computing. Visual effects is more and more happening in all the content that we see. That's where major part of supercomputing is going to be used. So I think the demand is going to be 10x or 20x in next 5, 6 years. Yeah.
Very good. Any other thoughts?
Yeah, to add to what Sanjay sir was saying, right now, from the processor perspective, we are working on RISC-V, and after spending the entire yesterday and today, I mean, it adds more confidence in us that whatever path we have chosen is really right, and that we are going in the right direction, and we are contributing in whatever small way we can. We are also contributing that. Right now, we have developed a series of processors which are for embedded class, which we call Vega. So we have now got 5 variants in place. So 2 of them have been into silicon, and we are working on the third one. So going forward, we see a lot of future in this. The government also is pitching very hard on this, the Digital India RISC-V program. So we are able to associate a lot of startups. Yesterday we heard a lot of talks on verification. So in fact, we are already engaging with a startup in the verification space, and we are now able to engage with startups who want to engage with us, take our processor IP, build their applications. All that is happening. So I think it's the right time to be in this space. Thank you.
So maybe just one point to add to what the CDAC leadership team spoke about the HPC thing. So what I really feel like from a perfect user perspective, often we get a little bit tied up with hardware architecture, hardware intricacies. We talk about performance, we talk about scale. Okay, so when we are talking about HPC, definitely there's performance and there's scale, but I think it should not be a bottoms-up approach. It should be a top-down approach. looking at the kind of applications, the problem-solving things that we have in India, okay, so the HPC as a solution with the operating systems, with the platforms, with the tool chains, everything together should cater to those requirements. Because often I feel like as engineers we get stuck with, okay, we are working on the hardware. Somebody may say we are, but the user disappears in the behind the curtain. So we need to keep the perspective of the user. And I think there are a couple of programs which Thales is also involved in. Maybe I can talk later on. So it's kind of the open compute where we are using RISC-V massively for server-grade microprocessors. Okay, so it's a different program apart from the embedded programs that we have within Thales. But maybe, I mean, there are a myriad of applications in India which actually demand the HPCs. And if it happens on RISC-V with a combined ecosystem, just nothing like that. So wish you all the very best and looking forward to having more interesting things from the CDAC team.
So I have a follow-up question. I was talking with someone just yesterday at the conference, and I'm going to go off script a little bit, but it's okay. When I joined, we got a huge liability insurance policy. And so what this person was telling me here at this event was they were lamenting that if you look at the pharmaceutical industry, if you look at the software industry in India, India supports other ecosystems, but isn't the center of gravity sometimes in those ecosystems. And they were lamenting that in the server space, in the data center HPC space, we'll build technology, but we'll ship it to Europe, we'll ship it to America, we'll ship it to Asia, and we won't have a Google-class data center here or an Amazon-class data center here. What do you four professionals say about that, and where is India going, and how do they get there? Go ahead.
Okay, so let me take the lead for this question. So I think when it comes to the data centric approach, okay, if we talk about the strategic sector, the view is completely changing now. Okay, so including DRDO as well as the space organization, they're looking for their own data centers. And if it happens, then definitely there's a lot of qualifiability, reliability, confidentiality that will be needed. So in that case, I mean, people who are working with RISC-V on the HPC side, on the, for data centers, for servers, okay, that's definitely a plus. Because to the extent that we know from Thales, I mean, what's going on within the strategic sector in the country, there's definitely a need for private data centers, and that cannot be a Google data center.
Good. I just a quick follow-up. So I wanted to go into now turning the conversation towards how RISC-V can help. So there are obviously barriers and challenges to get HPC running in India. Some of them are so pervasive, they're like energy issues, water issues, transportation issues, other things like that, that I may be missing the mark. I don't think RISC-V can probably help there, but maybe there's smarter people than me that think that's not true, and maybe one of you can talk to that. But there are other things, and it was talked about in the panel this morning about innovation and flexibility and reuse and cost and total cost of ownership. Where do you see RISC playing its role, and how do they address the things that keep you guys up at night as you build your businesses?
So I think we had discussed in previous speakers have also discussed that innovation is possible in RISC-V in many ways. And I think in HPC, as we have seen in one of the slides of Professor Mateo, that the efficiency of the supercomputers in terms of the application performance is only 2 to 3%. Okay, if you compare to the peak performance what is available. So a lot of innovation is required, co-design is required in this HPC space to get the best possible performance from this processor. So RISC-V is actually ideal thing where we can, the people can innovate, put new architectures, new features, application-specific instructions, and maybe application-specific accelerators also, possibly in the single chip. That is what is a requirement to get this kind of efficient architectures. And that is actually very much possible with RISC-V because of openness which is available.
Any other thoughts on that?
My thoughts won't be focused on HPC. Okay, so what I would like to add to what Sir was saying is that not only HPC, we find a gamut of applications where we need a processor. India is a huge country, there are a lot of applications. not even in consumer, in defense we are now engaging with defense as well as strategic partners also, where they need they have very specific requirements. So there, right now they're using commercially off-the-shelf components, which may not be actually targeting their exact requirement, but they live with it. Like we had an earlier talk, somebody was saying that you build you buy a cord stuff, a lot of garbage in it, we don't need it. Similarly, they have to live with it. Now we are in a scenario where we are engaging with them, we are working with them to build solutions specific to their requirements. That's all possible because that we can build processors, we can customize whatever we're having to cater to their specific requirements. That's all possible because of RISC-V. Yeah, thank you.
Excellent.
Yeah, can I go back to your previous question and then answer this question as well?
It will cost you.
I'll pay.
No, please go back.
So while I was trying to build my own supercomputing architecture, the biggest hurdle that we've seen and where I think it needs maximum addressing is that density part of the data centers. Current data centers wouldn't push themselves beyond 3 kilowatt or 6 kilowatt per rack. And the kind of supercomputing we are talking about, and with the kind of real estate cost and everything put together, I think data centers needs to go, in my experience, I'm not too sure, whatever I've seen so far, they can't go beyond 10 kilowatt. And I've seen European or American data centers are almost pushing themselves beyond 10 to 20 or 30 kilowatt or 50 kilowatt per rack density. So that's a place where I think data center needs to look at Indian data centers, because most of the commercial data centers give you 3 kilowatt. And today, if you get a good high-performing computer with a bunch of GPUs inside, one server itself will take 3 kilowatt. So entire rack, you can't just put one server. That's a full waste of space. Yeah, so that is the area where I think data centers really need to think and see how they can take it forward. Yeah.
Excellent.
I agree with the other panelists. I think co-innovation is the key. So it's not just innovating on ourselves, as Dr. Krishna rightly pointed out. So since we are working for the customers, since we are working for the community, okay, so we really need the users and the customers to come onto the same floor and co-innovate along with the developers. That is what is going to make this technology more effective for the future.
Yeah, and that's what was brought up at the panel this morning. And it's something that in the last 20 years I've noticed with working with some of these big companies, which is could be a good segue into a question that I have 2 questions from now. It's really hard to get that flexibility, that partnership, that co-innovation with an NVIDIA and Intel. I mean, they're great companies, right? Or an ARM. It's not profitable for them to do that. It's not part of their business plan, and they don't want to support it. And RISC-V has the ecosystem to do that. You guys would agree with that statement? Yeah. All right, so most of my career I've spent as a business guy. By the way, by show of hands, how many people in the audience are engineers building product, doing engineering stuff? Engineers? How many folks are business guys? So we got quite a few business guys in the audience too. So we'll throw a little bit of love out to the business folks. So all my life I've been involved largely in strategy and building new businesses or expanding businesses in new areas. And I watch trends. And some of the trends that are happening right now, we've never seen before. It's going to change the game. How? I don't know. If I knew, I would have bought Dell stock and Apple stock a long time ago if I could predict the future. I can't. But costs are going up. I've been hearing that in the next 3 to 5 years, with 18 angstrom coming online, 14 angstrom, we could be seeing $50,000 wafer prices. I have heard Moore's Law, and I've seen Moore's Law slowing down. We can debate that, but it's slowing down. And then I've heard that velocity, or I've actually studied and done a report that velocity of business is going up. I looked at how long it took for a telephone. The telephone, when it was invented, it took like 60 years for 150 million users to get the telephone. The TV was like 37 years. You start fast forwarding through all this technology. Skype was 1.5 years. iPad was 5 quarters. We look at ChatGPT now. I think they hit 150 million users in months. So the market moves radically now, and new markets are created out of nothing in months. Yet if you're a silicon guy, you have to tell your customer, well, we'll have that technology in 5 years. So this is kind of like a dual question around chiplets and RISC-V and the flexibility of RISC-V. Given these trends, and the fact that it is an open ecosystem, Linux is to Windows what RISC-V is to ARM and x86. Does this RISC-V dynamic really help you win versus the competition in this new market dynamic we're facing with these new trends that, by the way, we're experiencing in many cases for the first time in 60 years?
Again.
Did I talk too much? I feel like I talked too much.
All right.
I mean, basically, I'm from the application side, right? So as he said, I'm from the top down, not the bottom up. Any innovation will generally take time because not only the hardware, but the software and then the applications and the users, right? So in our industry, one of the open source software which is very popular, which is not very popular but very good, produces great result it's called Blender. Adaptation is very slow. It's free. Nobody has to pay for anything. There is a beautiful forum out there which all the help available. Problem is the users have to adopt it. So that is the bottleneck there. It is not the technology or it is not so how quickly we get users to adopt it is going to decide how quickly it seeps into the systems, right?
And are you seeing adoption happen faster, or is it just as fast as it was before? Are you seeing acceleration in the velocity of business?
I think it's happening faster now, but it's still slower than what is expected, right? Like as you said, difficult to work with these tech companies.
Yeah.
Because they have licensing and very complicated way of working. So open source software, which works beautifully, produces great result, but there are less people adopting it because of less awareness or less channels from where they can expose, and some big company should adopt it. So it's like then the trend starts. So we are kind of pushing people to go open source and use it. So I think I have no clue about chip manufacturing or chip designs, but I think that's the same thing rule will apply in adaptation of RISC-V. Yeah.
You got me thinking about a ton of stuff, but I don't want to be unfair to the other panelists and talk to you for the next 4 hours, so we can take this offline. But
Sure.
You've got me thinking about, I have to build these business models in line with what you're talking about, the pros and cons, the challenges, the weaknesses. So we'll talk offline. So I want to go back to the question again too on RISC-V is, does this open business model help you? And given the trends you see in the industry, is it something that is naturally pushing you towards RISC-V with benefits?
See, this open source software, I think we are seeing the fruits of it. I think everybody is looking for open source software because not a single company can actually make the full system out of the today's world. So open hardware is actually now picking up as RISC-V is coming up. OCP is another one which is on the system level. So I think it is going to be much faster than earlier, the adaptation of this and RISC-V can come up very fast. In last 2-3 years, I'm seeing a lot of momentum. And I think all the community has to work together to make the full software ecosystem available on the RISC-V thing. Because I've seen that ARM started way back for server related ICs from I think 2012-13, but still it is not in the mainstream processor because of mainly on the software ecosystem, because the open source community was not actually that much working on this ARM ecosystem, ARM software ecosystem. But I see and RISC-V open source community is growing much faster, and RISC-V I think has definitely advantage of getting into this server market as well as the HPC market quickly.
Yeah, certainly. Fully agree with Sanjay sir. We have a robust, let us say somebody wants to start on RISC-V, already you have a lot of open cores available, you have the compilers, everything in place, so you can download and start playing with it immediately. So already a robust ecosystem in place, and it's only a matter of time. Plus we have got a lot of startups, as I mentioned, working in this area. Not only you want to design products based on RISC-V, but there are companies who are startups whom we are ourselves engaging, who are in niche areas like verification, so are bringing a lot of value on board. So we are really confident that going forward, risk is going to be taking off great in the coming years. Certainly, no doubt about that. Yeah.
Well, I have a different perspective. So when we talk about a market, okay, we talk about customers, users, and people who are developing something and offering a service, isn't it? So how good or bad it will be when you are doing something which the customer really doesn't understand? It can be really good, it can be a game changer, but it adds no value to the customer if the customer doesn't really appreciate the value of it. Okay, so the value is always defined by the user, by the customer. What I felt within this small journey of my RISC-V within Thales is that users need to be educated more and more on RISC-V. RISC-V is not a technology. It's an architecture specification, and then you can use it for several different purposes. Okay. Again, RISC-V is open and free. So if we are talking about strategic sectors like defense and space, where we already, companies like Thales have decades of established business, okay. But it becomes so difficult to push forward, with RISC-V based solutions because it's from both ends. Okay, so from the user, it's like, hey, you said it's free and it's open source. So that's a problem. And on the other side, on the business side is, oh, the customer says that they don't see a value in it. Then how can I see a value in it? Okay, so okay, it can be a good thing for somebody else, but it's not good for me. So it becomes very difficult, to think in terms of bringing a change when the two parties are inadequately informed or educated. So I think with more and more RISC-V forums coming up, more and more such conferences, this is happening slowly. But yes, this needs to happen a lot, okay? Because the moment we talk about open source and then free, then the interest from the customer's side really dries up, okay? But the benefits of RISC-V are really on the side of the openness. Again, so the curse of openness is a blessing as well. Okay, at least I can say, like, if we are talking about certification, which is of a major value for our product lines, because we deal in defense, we deal with aerospace products, okay, technologies. So certification is in the DNA of our product lines. So if we are talking about certification, how do you certify a hardware? Okay, I can have an ARM chip. No, nothing adverse against ARM and established microprocessors. But the fact remains a fact. Like, if I want to deliver a qualified, a certified solution end to end with certification at each level of the system, starting from the hardware till the application end, a full stack certification, it's impossible because I don't know what's inside that black silicon chip. But with RISC-V, it's really a game changer for us. But
so the transparency helps.
Yeah, the transparency. But again, that education is really important.
And it seems like that could be.
Can I add to that?
Yeah, absolutely. Go ahead.
So I fully agree with what Sir was saying about this because there is always apprehension. It's open source, but because we are now working with at least 2 strategic customers, I would say. I'm confident in saying that they have understood the need of the Atmanirbharta. So they are using COTS components now, but they are now moving on to an indigenous technology because, like you said, they are understanding that RISC-V SA is open source. The implementation is going to be done by an Indian company, so they can have full confidence in the design. And when they engage with us, there's no hidden agenda, right? The design is fully transparent, and the design is owned by them ultimately. So that brings in the confidence to the strategic sector. So I understand it's a long way to go. Yeah. I would say we are doing baby steps, but I feel that we are there. We are going to start, and we're going to go ahead in a big way. Yeah.
So in addition to that, maybe if I have got a few more minutes.
No, please go. I have found that from American reality television and talk shows that when a fight breaks out on stage, the viewership goes way up. So I really, really want to see more conflict here. And this is going in a great, great direction, right? Good. Let's go.
However,
Let him have it. Let him have it.
But Keith, we are not conflicting with each other, unfortunately. We're just supporting each other. Okay, so the additional point that I would like to say is, I feel we are putting a lot of emphasis on the hardware part, honestly. Okay, when I open the LinkedIn every morning, I see, there's a famous personality, John Round. Okay, I keep following him. He's from that embedded world or something like that. And every other day, one RISC-V core or microprocessor or design or IP is coming up. Okay, but unfortunately, I don't know. I mean, definitely my knowledge may be limited on the software side, but the equal pace is not really observed on the software side. And when I say software, I mean the tool chain, I mean platforms, okay, which would come up more and more supporting these hardware infrastructure. Say, for instance, I can give one example. I'm interested in the vector extension, but unfortunately, I can't find, too many compiler options which can support the vector extension for my RISC-V design. Where do I go? I had a discussion with Eddie, okay, and there was only one question like, do you also, or can you, when I proposed, like, okay, sir, we are working on RISC-V, so we can give you some RISC-V designs based on FPGA implementation, and you know what? The interesting thing is that you also get the source code from us. Okay, no bright eyes for sure, but only one question. Can you also give us a compiler which can generate a qualified code for RISC-V? And I was just dumbstruck. Okay, they just shut my mouth up because I don't know how to do that or who does that. Okay, so I think we have to look at the counterpart world, the software world, when we talk about specifications like performance, safety, security. So that's my point.
That's
Yeah.
good. Well, we have 10 minutes, and maybe Bob will give me that look like wait for questions. So I'll be watching for him too. There's one important question I wanted to ask, and since we're kind of coming to the end of time, I'll skip a couple of questions and jump right to this one because I think it'll help the audience. And I think you segued into it perfectly with this discussion, which is I want to ask each and every one of you, when it comes to adopting RISC-V, what's the number one thing that keeps you up at night? And what can the ecosystem partners, all of which are sitting in this audience, what can their companies do to help you feel better about that concern? They'll be more successful by solving your most prominent problem. So tell me, and we've talked about it a little, we hit a couple things here, but just one, what is the big thing that keeps you up at night adopting RISC-V as a new piece of technology, and how can these companies make money by helping you?
I would say the outset initially, the challenge was 5-6 years back. Did we do the right choice initially? That was always a question we had initially when we embarked on this journey. But that question is now not keeping us awake, or no issues in that. Like yesterday, and today also the speaker spoke of verification is one major challenge we face. But what we are happy about is we've got a lot of open source stuff available using which we can build a verification environment. Plus, like I mentioned, there are a good amount of startups, companies who are of course, who have got a legacy experience from AMD, Intel, who come with a good experience. So they are also assisting us. So that challenge also we feel that we'll be able to surmount going forward.
Okay.
If From my point of view, if let's assume that there is a RISC-V server available which can do high performance computing, then only two things come in my mind. One is total cost of ownerships, and then other is applications. If RISC-V supports that, then I think I'll sleep at night peacefully.
Got it. So it's total cost of ownership.
Yeah.
And then run the software you want to run that customers are going to pay you for, and that's what you want to do.
Yeah.
So that is a little bit different than what the panel this morning says, which is really about flexibility, and cost still matters because money is fundamentally what we're doing in a business, right? So you would say, don't oversell the flexibility, and you own your own IP. Some people might like that, but the total cost of ownership matters. Make sure you're providing a really, really solid system from performance per dollar, power per dollar.
We are in a very competitive country. Indians like to bargain, so
Yeah,
cost of ownership is very important.
yeah.
Again, slightly different. So for me, it's the ecosystem support, which keeps me going on RISC-V. Every morning I wake up, I feel really excited to look into something new about RISC-V happening, some new partner joining, maybe the Open Hardware or maybe a RISC-V International. Okay, so I really don't think like we are doing some different things. The what part is not changing at all. I think what we are doing is we are working on the how part. So the difference is how we are doing certain things. The ecosystem, which probably it was there, but it wasn't so prominent as it is now. The software people coming together, the hardware people, the users, the customers. Okay, I mean, it's a combined network where people can talk freely, where people can breathe freely with their thoughts. Okay, so that's what keeps me going, and I think that's what is essential for RISC-V to keep going. And I think more than me, Celeste Redmond would wake up every morning with a bigger grin and a bigger smile on her face thinking about this, that the ecosystem is growing.
So there was a lot of ecosystem comments. I'll give you the last word, but there's a lot of ecosystem comments around, hey, am I getting the right compiler? The vector extensions. There's just too many choices. What do I pick, and how do I get support for that? So is there any one part of the ecosystem that stands out to you that is more maybe dangerous and frightening than anything else? Because there's probably a lot of entrepreneurs in the audience thinking, where are the hot spots where I can go start a company and really add value? Is there any guidance you can give to people that are saying, here's the hot spots in the RISC-V ecosystem? It's either this works well or this is not going to work. Is there anything like that, or is it kind of like there's a lot of places?
Okay, so if I take the lead for this question, then for me, it's a tool chain. We still need a lot of support on the tool chain. It's not just sufficient. Okay. If we really need to fully appreciate RISC-V, we have to work a lot more on the toolchain side and also on the platforms maybe. I mean, when we are talking about real-time operating systems, okay, definitely we need to look at it. Okay, it's not just FreeRTOS, it's not just Affair. Okay, so we have to think about more, which can be more specific towards the three specifications I talked about: the safety, security, and performance. So this is just another point, like I think what you touched base on. I mean, when we talk about RISC-V, we can really think in terms of specifications. Other than that, I mean, when we see a microprocessor, the only thing, the first question that comes onto my mind is how fast the microprocessor is. What is the operating frequency of the microprocessor? I forget about how safe the microprocessor is. I forget about how secure the chip is. But thanks to RISC-V, that RISC-V has helped us to think in terms of specifications that we can really segregate, and it's time that the software world can also think about that.
Okay, Sanjay, I'm going to give you the last word, but one thing. Where are our students in the audience? Any, by show of hands, students? Students, oh, cool, there's quite a few of them. So you just heard tool chain, right? So start a tool chain company, and since I help you, I need 10% of your company. Just kidding, just go get rich by yourself. It's okay. All right, Sanjay, wrap us up. I think we're out of time, right? Okay, Sanjay, take us to the end.
So I am actually from HPC background. So from HPC side, actually what we are looking for very low power processor, general purpose processor, as well as accelerator. Because we know that now we are talking about exaflop and now gigaflop later. So it has to fit in 20 to 30 megawatt of power, these kind of systems. So major thing what we need is basically low power CPUs. So that is one thing, because we know that the general purpose processors which are there now are having 100 plus cores, high performance core working in the single chip. And the power consumption of each chip is 350 to 400 watts. That is the current trend. So that is not sustainable because there are major problems in cooling and putting together many CPUs in one single rack. So that is one challenge what I'm looking for the solution. Second challenge is basically on the system level. It is not just specific to RISC-V. Is basically having a SMP machine, which is occupying complete rack, where many processors are working together as a shared memory system. So now CXL 3.0 is coming up, and I think that is what should be accommodated in the general purpose CPUs, so that one can have a SMP machine which can be a complete rack based, and then you can have a very good network between these racks to have very scalable systems. So these are the two things. And third thing is on the software side, that is the ecosystem which need to be developed for this process. So there are libraries need to be developed, which is math library and science libraries. That should be very optimized for the architecture. That is a major requirement of any HPC systems. So that I think the open community has to work together to get into this.
Well, this was an excellent discussion, and what often happens, I had 5 primary questions. I didn't get to any of the extra ones, but the 5 primary questions created like 50 more questions, right? Which often happens when you get into these kind of issues. So hopefully we'll continue talking about this. We will build the ecosystem that will make RISC-V successful. It doesn't happen overnight, and it requires a lot of, like you were saying, cross-collaboration, and no one country is going to be able to do this. So India is going to play a pivotal role in all of this. So let's thank our panelists. This was a great discussion, and thank you all. Awesome. Thank you so much. Hope you had some fun. Good, good. Thanks.
Thank you. You did really well. Thank you.
Thank you so much, man. That was really insightful.
I was hoping that we were going to go after each other. Can I get some help off stage?
Hey, thank you very much.